Hi, everybody. It's Professor Mitchell, continuing with Chapter 10. Today, we're looking at Section 10.2 on infinite series. Infinite series will actually be the topic of the rest of this chapter. So they're going to be with us for a few weeks. All right, so as an introduction, let's talk about, does it make sense to talk about an infinite sum like the one you see here? 1 plus 1/2 plus 1/4 plus 1/8, continuing on and on and on forever. Well, the way that we try to make that make sense is by talking about a sequence of partial sums. The first partial sum is S1 is just the first term whose value is 1. And I'll talk about this column over here in just a minute. The second partial sum is the sum of the first two terms. 1 plus 1/2 is 3/2. The third partial sum is the sum of the first three terms. 1 plus 1/2 plus 1/4, which is 7/4. And in general, the nth partial sum is the sum of the first n terms. Here you have to be a little careful. 1 plus 1/2 plus 1/4, blah, 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 up to 1 over 2 to the n minus 1. So maybe take a moment to convince yourself that n minus 1 is correct here, that it shouldn't be n. Well, now if we go over to the column on the right, they're rewriting each of these partial sums in a way that makes the pattern easier to pick up on. If you write 1 as 2 minus 1, and then write 3/2 as 2 minus 1/2, write 7/4 as 2 minus 1/4. And for the last term, notice what, or for, I'm sorry, for the nth partial sum, notice that you can take this expression here and break it into two fractions. 2 to the n over 2 to the n minus 1 is 2, and then minus 1 over 2 to the n minus 1. Now imagine we let n increase without bound. If n increases without bound, this expression gets closer and closer and closer to 2. In fact, this sequence of partial sums converges to 2. So for that reason, we say that this infinite sum is equal to 2. All right, and you might have some trouble wrapping your head around that. A lot of people do. They want to say, well, yes, it comes very close to 2, but does it ever actually equal 2? Well, it comes very, very close to 2 anytime that you cut off the sum after a finite number of terms. But we do say that this infinite sum is equal to 2. We say it converges to 2. All right, so here is the full definition. Bear with me for a moment here. Given a sequence of numbers a sub n, an expression of the form a1 plus a2 plus a3, da 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 da, plus a sub n, continuing forever, that part is very important, is an infinite series. The number a sub n is the nth term of the series. The sequence s sub n, defined by s1 equals a1, s2 equals a1 plus a2, and in general, S sub n equals a1 plus a2 up to a sub n, is the sequence of partial sums of the series, the number S sub n being the nth partial sum. If the sequence of partial sums converges to a limit L, we say that the series converges and that its sum is L. In this case, we also write a1 plus a2 plus a sub n, a1 plus a2, blah, 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 plus a sub n, continuing forever, equals the sum. Remember, in math, capital sigma means sum. Maybe you haven't seen that since Calc 1 and Riemann sums. Remember those? The sum n equals 1 to infinity of a sub n is equal to L. If the sequence of partial sums of the series does not converge, we say that the series diverges. All right, so in this chapter, we're going to be looking at a bunch of different types of series. And there are many types of series. Well, there are just a few types of series where not only can you tell whether the series converges or not, but also what its sum is. Unfortunately, after a while, we're going to have to be happy with just figuring out whether the series converges or not. We will not talk about how to find the sum of that series. That's either a topic for a more advanced math class, or in some cases, nobody knows how to do it. All right. But one of the types of series where, first of all, it's very easy to figure out whether it converges. And when it converges, you can find its sum, is called a geometric series. A series in which the ratio between two consecutive terms remains constant is called a geometric series. All right, so this is a theorem, and it's a theorem that I can't resist showing you the proof of. However, you'll be happy to know that I have the proof all written out, so don't have to spend too much time looking at it. If the absolute value of r is less than 1, then the geometric series a plus ar plus ar squared plus ar to the n minus 1, continuing forever, converges to the number a over 1 minus r. And another way of saying that is shown right here. Again, that's true if the absolute value of r is less than 1. If the absolute value of r is greater than or equal to 1, then this series diverges. So let me switch over to the tablet and spend just a moment showing you the proof of that. Again, it's one that I can't resist. I really feel like this is important enough that you need to see this. So I'm going to walk through this with you briefly. First, let's suppose that r does not equal 1, and I will treat the case when r equals 1 separately. And let's look at the nth partial sum of this geometric series. It would be a plus ar squared, up to ar to the n minus 1. And this is a partial sum, so this does not continue forever. So now what I'm going to do, because it's a trick that works, is I'm going to multiply both sides of this equation by r. So on the left side, I will have r times s sub n. And now look, because I think this is kind of cool. A times r is ar, which I will write over here. Ar times r is ar squared, which I write here, and so on and so on. When I get to the last term, ar to the n minus 1, and multiply that by r, I get ar to the n. So now what I'm going to do is subtract this equation, the second equation, from the first one. So on the left side, I get s sub n minus r times s sub n. Factoring out s sub n, you get s sub n times 1 minus r. And then I just think this is so cool. All of these middle terms cancel out and leave you with nothing but a, this a right here, minus ar to the power n. Okay, so s sub n times 1 minus r is equal to a minus ar to the n. So now is where r does not equal 1 comes in handy. If r does not equal 1, then I can divide both sides by 1 minus r. And at the same time, I factored a out of this. So that actually gives me an expression, a closed expression for s sub n. S sub n is equal to a times 1 minus r to the n divided by 1 minus r. Now, if the absolute value of r is less than 1, then that means that we're taking a small number and raising it to a big giant power. So as n increases without bound, this expression is going to converge to a over 1 minus r, and that's because r to the n approaches 0. That's if the absolute value of r is less than 1. However, if the absolute value of r is greater than 1, then you're taking a larger number and raising it to a big giant power, and that is just going to blow up. If r happens to be a positive number, then this will go towards positive infinity. If r is a negative number, then this is just going to oscillate between a great big giant positive number and a great big giant negative number. In both cases, that limit does not exist. Okay. So there's just one more little piece we have to talk about. At the beginning, we assumed that r was not equal to 1. So what if r is 1? Well, that case turns out to be very simple. If r equals 1, then this geometric series is just a plus a plus a, continuing forever, which, as long as a is any number other than 0, that series is going to converge. Imagine even that a is 0.01. If you added, 100 zillion terms that were each 0.01, that's going to turn into a great big giant number and will go off towards infinity. Okay. All right. So I hope I didn't go on about that too long. It would have been even longer if I had written that all out while I was talking to you. All right. Again, there are some proofs that I just can't resist. I think they're that important. All right. So consider this to be the first trick in our bag of tricks for series. We will try to identify geometric series very early on. Because they're very easy to deal with. So a couple of examples here and here. So let me switch over to the tablet. And we'll look at example 1a. The sum n equals 0 to infinity of 2 to the power n plus 1 over 5 to the n. So my favorite method for dealing with these is to write out the first few terms. I think that's the easiest way to do it. Okay, so the first term of this would be 2 to the first over 5 to the 0. The second term would be 2 to the second over 5 to the 1. Third term would be 2 to the third over 5 squared, etc., etc. Continuing forever. In other words, 2 plus 4/5 plus 8 over 25, etc., etc. So I claim that this is a geometric series. And the reason I know it's a geometric series is to get from one term to the next, you are always multiplying by 2/5. Okay. So since it is a geometric series and r is 2/5, and technically, I guess I should say the absolute value of r is the absolute value of 2/5, which is less than 1. That means that this series does converge. And it converges to the number a over 1 minus r. Remember, a is just the first term of the series. So let me label this number 2 as a. All right, so this would be 2 over 1 minus 2/5, which is 2 over 3/5, which is 2 times 5/3. This series converges to 10/3. Okay, so if you get bored for a minute, it's kind of fun to take your calculator and just start adding, as many terms of this series as you can stand to, and notice that as you keep adding and adding, the sum should get closer and closer to 10/3, which is 3.33333, repeating. Okay, so geometric series are pretty easy. Let's look at another example. 1 plus -3 plus -3 squared plus -3 cubed, etc., etc. This is also a geometric series, and I know it's geometric because to get from one term to the next, you always multiply by -3. So I should put these in parentheses. Well, this series is not going to converge because the absolute value of r, which is the absolute value of -3, is greater than or equal to 1. So when a series diverges, that's all there is to say. That means it does not have a sum. And I think that makes a lot of sense, at least in this example, because if you keep adding, 1 plus -3 plus 9 plus -27 plus 81, you're going to notice it just kind of flip-flops all over the place, does not get close to any specific number. In fact, it's the sequence of partial sums oscillates between heading off towards positive infinity and heading off towards negative infinity. All right, now one fun application of geometric series is repeating decimals. And I have often said that there should really be some core math class where we cover repeating decimals, how to convert them into fractions. The only other class that I teach where I do this is Math 20A, which I call Math for Teachers. Mostly people that want to be elementary school teachers take that class, and we cover this in there. But this is a particularly fun example. So I bet it's possible that you have never thought about the repeating decimal 0.99999 repeating. You've seen plenty of other repeating decimals. I was just talking about 3.33333 repeating. So the question I would like to ask you right now is, what do you suppose the value is of this repeating decimal? And there are really only two reasonable answers. Do you think that this is just a tiny bit less than 1? Or do you think that it's actually exactly equal to 1? Right? So think about that for however long you need to. Decide what you think your guess is. I remember when I started graduate school, I was a teaching assistant for a Calc 1 professor. And on the very first day of class, he asked his students this question. It was a big, huge class with like 120 students or something. And he kind of made it into a poll. All right. So I'm going to show you how we deal with this. Notice that another way of writing 0.99999 repeating is as an infinite series. You can write it as 0.9 plus 0.09 plus 0.009, et cetera, et cetera. And if I wanted to write this as a geometric series in closed form, which I don't really have to do, maybe I'll do it just this once, it would be the sum, n going from 1 to infinity, 9 over 10 to the n, right? The first term is 9/10, the second term is 9/100, the third term is 9/1000, etc. Notice that this is a geometric series, and I know it's a geometric series because to get from one term to the next, you are always multiplying by by 0.1, right? Yeah, to get from one term to the next, you always multiply by 0.1. Hopefully, at some point in your schooling, somebody pointed out to you that when you multiply by 0.1, all it does is move the decimal point one place to the left. All right. Hopefully, I'm not the first person to tell you that. All right. So since the absolute value of r, which is the absolute value of 0.1, is less than 1, this geometric series converges. Repeating decimals will always converge as geometric series. And it converges to the number a, whoops, that's what I get for trying to talk and write at the same time, to the number a over 1 minus r. Remember, a is the first term, so in this case, it's 0.9. 0.9 over 1 minus 0.1. Oh, wow, look at that. Are you surprised? 0.9 divided by 0.9 is equal to 1. Moral of the story, the repeating decimal 0.9 repeating is exactly equal to 1. And that's why it's likely that you've never seen this particular repeating decimal before, because we just always write it as 1, right? For those of you who are math majors, when I was in graduate school, I think it was the first time it came up, the fact that there are actually 2 different ways to write every number. For example, 1 can be written as 1. It can also be written as 0.9 repeating. Actually becomes a little something of a headache in certain proofs. And so you have to start the proof by saying, okay, this is how we're always going to write our decimals. And believe it or not, in the proof I'm thinking of, we agreed ahead of time to always write them as repeating decimals, right? Ending in 9s. It turned out that that was the easiest way to do it. All right, now this one is a little more complicated. So what I'm going to do with this one is forget about the 1 at the beginning, just for now. And I'm going to concentrate on the decimal part, 0.414 repeating. So that can be written as 0.414 plus 0.000414 plus 0.00000414, et cetera, et cetera. This is, again, a geometric series. And this time the value of r, let me see, I'm probably overthinking this, but if you take a decimal point that's here and move it 1, 2, 3, that means that r, to get from one term to the next, you would multiply by 0.001. Right, 0.1 would put it 1 place to the left, 0.01 would put it 2 places to the left, 0.001 puts it 3 places to the left. And that is how you always get from one term to the next. All right, and here's the value of a while I'm writing in blue. So since r, the absolute value of r, which is the absolute value of 0.001, whoops, darn it, is less than 1, this series converges to the number a over 1 minus r, which is 0.414 over 1 minus 0.001, which is 0.414 divided by 0.999. Now, if you multiply the top and the bottom of that fraction by 1,000, you get 414 over 999. And I know I can reduce that or simplify that fraction because I can see that both of those numbers are divisible by 9. Okay, and I think that's the best we can do. 414 over 999 simplifies to 46 over 111. Now remember, darn it, we're not quite at the final answer because we took that 1 off at the beginning. That was not part of the repeating pattern. That's why I took it off. So let me just make a little bit of room right here where I can say that the repeating decimal 1.414 repeating is equal to 1 plus 46 over 111. which if you write that as an improper fraction is 157 over 111. So that's typically what they're going to ask you to do, is to write these repeating decimals as fractions in lowest terms. All right, back to the presentation.